For decades, two identical NASA spacecraft appeared to be violating the laws of physics. Launched in the early 1970s to explore the outer solar system, Pioneer 10 and Pioneer 11 were slowing down more than they should have. The effect was very small, almost immeasurable, but it was real, consistent, and unexplained. Both probes exhibited the same strange behavior at roughly the same distance from the Sun, as if an unknown force were pulling them back. Scientists dubbed this the Pioneer Anomaly, and for nearly 20 years it remained one of the most mysterious secrets of deep space exploration. Some wondered if it pointed to a new law of physics, perhaps a distortion of gravity at great distances, or an effect of cosmic expansion we don't yet understand. Others suspected something simpler but harder to detect, an overlooked engineering detail in the spacecraft's design. When the answer finally came, it required the recovery of decades of data, the reconstruction of detailed thermal models of 40-year-old hardware, and years of meticulous analysis. This is the story of how the Pioneer Anomaly was solved, not with exotic theories, but with patient and meticulous science. NASA launched Pioneer 10 in March 1972 and Pioneer 11 in April 1973. These were pioneering missions designed to be humanity's first envoys to the outer solar system and beyond. Pioneer 10 became the first spacecraft to fly past Jupiter in December 1973, sending back stunning images of the giant planet and its moons. Pioneer 11 followed suit by flying past Jupiter in December 1974 and became the first spacecraft to visit Saturn in September 1979. After their planetary encounters, both probes continued on outward trajectories that would eventually carry them into interstellar space. They were spin-stabilized, meaning they spun continuously to maintain pointing accuracy without frequent thruster firings. This design choice would later prove critical for detecting the anomaly. As part of routine mission operations, NASA tracked the spacecraft using radio signals. Engineers on Earth sent signals to the probes, and the spacecraft sent the signals back. Scientists were able to calculate the spacecraft's speeds and accelerations with extraordinary precision by measuring the frequency shift in these signals due to the Doppler effect caused by the spacecraft's motion. This technique, called Doppler tracking, is sensitive enough to detect movement changes equivalent to a few millimeters per second over months. This precise tracking revealed something unexpected. When Pioneer 10 and Pioneer 11 reached a distance of approximately 20 astronomical units from the Sun, roughly twice the distance from the Sun to Saturn, their movements began to deviate slightly from predictions. The spacecraft was still moving outward, but it appeared to be slowing down slightly more than expected. This deviation was extremely small, approximately 8.7410 meters per second, or about 25 square feet of additional deceleration per day. At the spacecraft's speed of over 27,000 miles per hour, this was almost imperceptible. However, over months and years of monitoring, this deviation became a measurable effect. More importantly, both spacecraft exhibited the same anomalous behavior. This ruled out random errors or malfunctions specific to one probe. The consistency of the effect made it scientifically significant. Two identical spacecraft, launched a year apart and following different orbits, exhibited the same unexplained acceleration at similar distances from the Sun. This could not be dismissed as noise or a one-off glitch. A serious investigation was launched in 1994. Scientists examined all known forces that could affect the spacecraft: the gravitational pull of the Sun, planets and distant stars, the pressure of solar radiation, the friction of the thin interplanetary medium, even magnetic fields. All these forces were already included in the navigation models. However, the anomaly persisted. When all known effects were accounted for, both spacecraft were thousands of kilometers closer than they should have been. This raised a profound question. Was there a problem with the models, or was nature behaving differently than expected at these distances? Both possibilities were explored in the initial discussions. Some researchers wondered whether gravity deviated slightly from Newton's inverse square law at distances beyond 20 AU. Others considered whether this effect might be linked to general relativity, dark matter, or even the expansion of the universe. These were not wild speculations. They were legitimate scientific hypotheses, attempting to explain real, unexplained data. However, more conservative explanations were also investigated. Engineers began to re-examine the spacecraft in detail, searching for overlooked engineering effects that could produce a small but constant force. One of the main focal points was thermal radiation. The Pioneer probes were powered by radioisotope thermoelectric generators, RTGs, which converted heat from radioactive decay into electricity. These generators continuously produced over 2,000 watts of waste heat. The spacecraft's electronic devices added about 100 watts more. All this heat had to radiate into space. According to basic physics, radiation carries momentum. When a spacecraft radiates heat, the photons carry not only energy, but also a small recoil force. If heat radiates equally in all directions, the net force is zero. However, if the radiation is irregular, anisotropic, it creates a small but constant thrust in one direction, like a very weak continuous thruster. The challenge here was to determine whether this thermal recoil force explained the Pioneer Anomaly. This required detailed information about the spacecraft's geometry, material properties, and temperature distribution, information that was difficult to reconstruct decades after launch. Early navigation models simplified these details, focused on dominant forces, and deemed thermal effects negligible. But what if they weren't negligible? What if a small anisotropy in heat distribution, just a few percent, was enough to create the observed effect? To answer this question, scientists needed data. Fortunately, the Planetary Society stepped in at a critical moment. In the mid-2000s, a team led by Slava Turyshev at NASA's Jet Propulsion Laboratory learned that Pioneer Doppler data and telemetry had been stored on decades-old magnetic tapes. These tapes consisted of hundreds of 7- and 9-channel tape reels that had become unreadable due to media degradation. With the support of Planetary Society members, the team recovered and digitized over 30 years of navigation data collected from both spacecraft. They also recovered engineering schematics, thermal data, and temperature readings taken during the missions. This valuable treasure trove of information made it possible to create a comprehensive thermal model of the spacecraft. Using finite element analysis, the team recreated how heat was generated, how it was conducted throughout the spacecraft structure, how it reflected off surfaces, and how it radiated into space. By simulating the thermal environment at various distances from the Sun, they accounted for changes in RTG power output due to the radioactive fuel's decay over time. The results were striking. The thermal recoil force matched the Pioneer Anomaly almost exactly in magnitude, direction, and temporal behavior. The anomalous acceleration was toward the Sun because the RTGs were mounted on booms behind the spacecraft's main dish antenna. Heat from the RTGs was reflected forward by the back of the dish, creating more radiation pressure in the travel direction than in the opposite direction. The electronics box at the front of the spacecraft also radiated more heat forward than backward. These asymmetries combined to create a small but constant recoil force against the spacecraft's motion, which is exactly what the Doppler data showed. In June 2012, Turyshev and colleagues published their findings in the journal Physical Review Letters. When the thermal recoil force was correctly accounted for, they concluded that there was no abnormal acceleration. This inconsistency did not arise from new physical laws. It stemmed from an engineering effect that had simply been overlooked in earlier models. The anomaly was real in the data, but its cause was conventional. The solution to the Pioneer Anomaly holds important lessons. First, it shows how extremely small forces can create measurable effects over long time periods in deep space. In environments with few external influences, even weak effects can become detectable signals. Second, it emphasizes the importance of detailed spacecraft modeling. Modern missions now incorporate much more sophisticated thermal and structural simulations thanks to lessons learned from Pioneer. Third, it shows how science responds to unexplained data. The anomaly was not ignored or dismissed. It was seriously investigated, openly debated, and meticulously analyzed over many years. Numerous hypotheses were explored, ranging from exotic new physics to mundane engineering effects. The solution came not from speculation, but from better data, improved models, and a deeper understanding of the spacecraft themselves. The Pioneer Anomaly is now considered a solved case. It no longer challenges gravitational theory or cosmology, but it remains an important lesson in the value of precise science and perseverance. The story of Pioneer 10 and 11 is not about discovering new forces in the universe. It is about how scientific understanding evolves through patience, evidence, and the careful refinement of models. The anomaly was real. Its cause was not new laws of nature, but simple physics, and solving it required 2 decades of work, data recovered from old tapes, and scientists who refused to give up on the mystery.